In this video, we'll be covering the concept or the algebraical concept of partial fraction decomposition. Now this will come up later again in Calc 2 in terms of how to manipulate things so that you can integrate them appropriately. But for right now, we're just going to do the algebraic steps in terms of decomposing a single fraction into two fractions. Well, the way we're going to start this is by talking about what if I were to try and subtract these two particular fractions? Well, what I would first have to do is identify what their common denominator is. So I'd multiply top and bottom of that first fraction by x plus 2. That would allow the first fraction to have a common denominator with the second fraction when I multiply that second fraction on top and on bottom by x minus 4. So if I were to do this, this would provide me with on top 3x plus 6 on the first fraction. On the top of the second fraction would be a 2x plus 8. And I'm going to go ahead and leave it as two separate fractions for a second here to emphasize the importance of that subtraction sign sitting between the two. So when I'm doing this, every time that I find that common denominator between two fractions, and there's multiple terms on either top, I should really put parentheses around the entirety of the top of that fraction. So when I do this, I can go ahead and have on the top of a single fraction with that common denominator, this particular situation, all divided by x plus 2 and x minus 4. When I simplify the top, I'm going to go ahead and distribute that negative and then combine like terms. So I'm going to have 1x, 3x minus 2x, and then 6 minus 8 is going to be minus 2. So that is the top of that particular fraction. And on the bottom, if I were to FOIL this whole thing out, I would end up with something along the lines of, I'm sorry, I made a mistake. 2 times 4 is a negative 8. That means that this is a negative 8. And this, when subtracting, is going to be plus 14. Just to clarify that up. So again, distributing the 2 gives me 2x minus 8. 2x minus 8 when distributing the negative gives me negative 2x plus 8. So that 6 plus 8 is going to be 14. So now I have this, and then when I go ahead and FOIL out the denominator, I'm going to end up having something along the lines of x squared minus 2x and then plus, sorry, minus 8. That's a minus sign. And the question that ends up coming up in the calculus portion is more or less, how can I take this thing and get it back to that? That's the idea, is how do I take this thing and get it back to that? Well, in terms of partial fraction decomposition, the idea is I want to tear this fraction apart. What I do know is that if I can factor the denominator, which we do, we factor into x plus 2 and x minus 4, that if I can factor into that denominator, then in some way I know that those two denominator factors have to be the denominators of two separate fractions. Now this isn't always true, but it's generally the concept of how things work in terms of adding multiple fractions together. Our goal is to tear this thing back apart into those two fractions. So if we do this process correctly, we should end up with 3 over top of the x minus 4 and 2 over the top of x plus 2. Let's go ahead very carefully, I should say that very carefully, with technically a negative 2 over the top of x plus 2. So let's do this very carefully, but let's do this relatively consistently. What I do know for a fact is that if I'm starting off with x plus 14 and I want a partial fraction decomposition this particular problem, then I know it's going to start out as some kind of fraction of x plus 2, plus I know it's going to have some fraction of x minus 4 in the denominator. I know that those two factors in the denominator will create the factor or the denominators of my other two pieces, maybe more if there's more. On top, this x plus 14 has nothing to do necessarily with this top or this top. All it does is provide us with the end result when these two things are added together. What I do know, however, is that the top of this, if this thing is fully reduced, meaning the top power is a 1, the bottom power is a 2, the top power is never going to be or shouldn't ever be a larger power than the bottom, then we should automatically be able to say that if this is a linear factor, the top has to be a constant. Linear factor, the top has to be a constant. The reason I use a and b is because they are not necessarily the same constant. They can be different. So this is how we set up this problem. The next step to this problem is us trying to find out what A and what B are. There's a couple of ways that are relatively efficient in doing this. I do want to start off by phrasing it the way that it's really set up. Really what I want to do is I want to solve this equation for A and B. I want to solve this entire equation for A and B. Well, we don't really all that much care for fractions in this problem. So what I can do is I can go ahead and multiply both sides of this equation by the common denominator. So that's what I'm going to do here, making sure that the brackets are the original pieces. So I'm going to have a over x plus 2 plus b over x minus 4, but that whole side is going to be multiplied by x plus 2 and x minus 4. Now very carefully, this thing on this side cancels out with this thing on the denominator. So x plus 2 cancels out with x plus 2, x minus 4 cancels out with x minus 4. I'm left with x plus 14 on this side of the equation. On this side of the equation, I have that a plus 2, but I have an a plus 2, or sorry, x plus 2 and an x plus 2 here. But this thing has to be distributed to both this term and this term. So when I multiply the a over x plus 2 times both of these pieces, the x plus 2's cancel out, but I'm still left with the x minus 4. So it's a times an x minus 4. The next piece is plus b, and again, the b is going to be left over, but when I multiply this thing by this thing, the x plus 2 is going to remain because the x minus 4 on top and on bottom are going to cancel. So I'm left with this. So, when working with this, the idea is that I should be able to set up a systems of equations for this problem. I'm going to go ahead and set up the system, but we're not going to solve it using the systems of equations. I just want you to understand how this particular problem compares to that of your matrices examples. So the x plus 14 is going to remain unchanged. I'm going to distribute the a, so I'm going to have ax minus 4a plus bx plus 2b. I'm going to go ahead and rearrange this a little bit, so I have ax plus bx minus, or I'll do a plus negative 4a plus 2b. Now, these are the only two terms with x in them. If I factor the x out, I know a plus b times x. This side right here, a plus b, has to be equal to 1. I know that to be a fact because, well, no other terms of x are here, and this is the only set of values. The second piece is plus. This is my constant setup, so negative 4a plus 2b. I know that that has to equal to 14. So the system will be built in the same concept as 1 equals a plus b, and 14 equals negative 4a plus 2b. And now it's a systems of two unknowns and two equations. And we can solve that like we did in previous videos with these systems of equations problems. This is not the way that I'm going to solve this. I'm going to solve this in a much more abbreviated and, I think, efficient way. So the way I'm going to solve this is it's still solving this equation. I need to solve it for both a and b. I need to solve it for both a and b. So what I'm going to do is I'm going to go ahead and say this thing has to be true for all possible values of x. So can I find a single value of x that will allow me to eliminate one of the variables in such a way that I'll be able to find the other variable? Again, the idea is x is the actual variable, a and b are unknowns that I need to find. So if I choose to let x equal to, I don't know, negative 2, you'll notice that if I let x equal negative 2, this entire equation will change to negative 2 plus 14, so 12, equals a times negative 2 minus 4 is negative 6, plus b times 0, which conveniently enough then cancels b out. So now I know what a is. A, if I divide by a negative 6, a is a negative 2. That's a coincidence that worked out that way, that if I picked x equals negative 2, that a equals negative 2. But now I know what a is. This is going to be true no matter what x value I pick. It should still satisfy every single system that I choose to work with. Now let's go ahead and choose another x value. Let's restart back at this point right here and say, let's let x equal a different value. You'll notice now that if I let x equal 4, that my a term will turn to 0. So if I let x equal 4, that means I'm going to have 18, that's 4 plus 14 here, equals to, that's 0 a's, so that's going to cancel out, plus b times 4 plus 2, which is 6. And in this case, b is going to be equal to 3. So now I have a equals negative 2, b equals 3, and if I go back and I check that, my a, this equation right here, should be a negative 2 over x plus 2, plus my b is 3 over x minus 4. And sure enough, this is the exact same, maybe not the same order, but the 2 with the negative is over the x plus 2, the 2 with the negative is over the x plus 2, and the 3 that's positive is over the x minus 4. And sure enough, this does work in trying to identify what the fraction partially decomposes into.